Yeah, it says recording.
All right. All right. Well, good evening and welcome to lecture one for MT225 this semester. Traditionally, we'd be doing this in person, and I'm hoping to be able to do our next meeting in person. Right now, the issue is having a place to go. With the new hangar not quite available yet, as I found out this morning. I didn't know about it until this morning, since I'm not teaching there yet this semester. Um, and With the old hangar not really usable without a network connection, and no place on the Rome campus available to use, we're kind of stuck. So fortunately, I think we can get away with that tonight. As just an introductory lecture, but as we start getting a little more into board work and such, I'd prefer to actually be in a classroom, and hopefully we'll be able to secure something either on the Rome campus, or we'll get that certificate of occupancy going and we'll be over at the hangar. So typical class night will be starting out with our class notes. This one's a beginning class or an introductory class, so we've got to start out with some introductions. I think everyone who is taking this class is a current or former airframe and power plant student. So you all know me. You may not necessarily know each other. So we'll get a little bit of participation going here in a moment. But for introductions, we'll kind of go around the virtual room, I suppose, and see if we can get people to talk and share your name, where you're from, and now why you're here is a little bit of a different question, I suppose, when I ask it in the AMP program. When I ask it here, pretty much everyone has the same answer. I'm here because I need this course to get the associate's degree. So if you have some other reason besides wanting to be here for the associate's degree, or wanting to check the box for the associate's degree, feel free to share that there. But I added a little bit of a different question to motivate a little bit of discussion, I suppose. And that's what's something you might hope to learn or expect to learn or want to learn, either from this course or just something in general. If you have no idea what this course is about, which is a distinct possibility, as I usually get people asking questions about this math course. This is not a math course. This is an engineering course. And so you may not be entirely sure what this course is about, but if you know something about the topic of statics and strength of materials and have something specific you want to learn, feel free to share that. If you've got no idea what this course involves yet and can't really answer that question, feel free to answer it in general. What's something you'd like to learn, either technical or about AMP or about really anything. So let's see here. We'll stop the screen share for a moment and kind of go back. We got 4 people online here, so let's well, I guess we'll start with Doug, since he's the only one I can see and who's unmuted. So Doug, why don't you go ahead and give us a little bit of an introduction.
Well, my name is Doug. Um, I'm from Syracuse, right outside of Syracuse. I was in the military for 4 years. I was a car mechanic for the past, I don't know, 16 years, and now I'm pursuing fixing airplanes. As far as this course, I'm not really sure what it's about. I just, I had some college courses already under my belt, so figured might as well work for the associate's degree.
All right. Yeah, we'll go over tonight basically what the course is about, so everyone will get a pretty good idea about that. Let's see. How about we go to Kevin next? Kevin, are you with us?
Hey, how you doing?
Hey, Kevin.
My name is Kevin. I graduated a year ago from the program, working at Piedmont in Albany. I am not sure what the course is about, but I'm just looking to expand my knowledge in aviation and anything possible.
All right. Well, one of the advantages of this course, there is an this course is taught both with the for the associate's degree in aircraft maintenance, but it's also set up for other certificate programs and degree programs. The advantage to taking it with me, I suppose, versus other instructors is I try to use a lot more aviation related examples. A lot of times you can get tied up in basically working with bridges and bridge structures in this kind of course. But we'll look at, as we get toward the end, we'll look at things like wings, spar structures, bending and deflection, and all of that. So we'll get a pretty good idea of how these structural ideas adapt or are applied to aircraft. Thanks, Kevin. Let's see. How about Stephen?
My name is Steven, and I'm from Horseheads, New York. And I'm doing this basically because I think it's interesting. And what I want to learn is what you have to teach me.
Oh, very nice. Thank you. Well, for a change, you're the only Stephen in the class. So no others we have to worry about. We in the for those who aren't familiar with it, the class that Stephen's in has 3 Stephens in it. So we don't have to
4 Stevens.
4 Stephens?
Or well, the one is a Christopher, but
Yeah, he's kind of a virtual Stephen.
Yeah.
All right. And Phil.
Yeah, my name is Philip. I'm from Frankfurt, New York. I just recently graduated high school this past summer. I don't really know what this class is about, but I'm interested in learning something new. And but my priority is just to get the A&P license first.
Yep. All right. Well, let's get moving then. So back to the lecture notes. There we are. So how our normal class structure goes, or how our normal class session will go, is we'll start off with a little section on administrative details, things about the operation of the course, any notes I have on it, things you might need to be aware of. I refer to this as administrivia, just a little bit of trivial detail to take care of before we get into the bulk of the class. Then there'll usually be some review of the current topic that we're working on. If we've got a homework assignment out, then I'll ask for any questions there might be on homework, and then we'll proceed into whatever the content is for that evening. Usually introducing some ideas and then working some practice problems. You might have noticed this class is split up into a lecture and a lab, and that the timing is a little bit strange. I'm not exactly sure where their timing comes from, but we are going to be changing that slightly just to make it a little bit cleaner once we have a classroom to be in. We'll probably back that off to a nice even 5 o'clock instead of 5:10, and we'll be done at 7:30 instead of 7:40. I don't know why they couldn't just have shifted that 10 minutes, but that's where they are on that. The lecture component is where we'll discuss the ideas for the day and work on some practice problems. In the practical section, or in the lab section, what we call a practicum session, is where you get to practice on solving the problems. Traditionally, we do this in the classroom. I'll put a problem up on the board, and then I'll wander around and I'll look at your attempt at a solution individually, see where you might be going wrong, or give you feedback on that solution. A lot of times I'll put the answers up on the board, and when you've got the answers, you've solved that problem. So there's a lot of problem solving involved with the course. Today we're going to go over the course expectations and course content a little bit. We'll go over the divisions of this science we call mechanics, and we'll be breaking there before we get into the real content for the class next Monday night. So some of our administrative details here. First thing I have to get to is our course syllabus, and the course syllabus is on the course website, which is, let me flash ahead to the URL here. The URL is right here for the class website. It's www.keytool.org/MT225. This is on one of my servers. If for some reason my network connection is a problem or something like that, or something happens during the semester, I do have a Blackboard site available that we could move everything onto, but usually I find that to be more hassle than anything else. So I just use my own server for that. And if we go over and take a look at that for a second here, let's see, there it is. The website is nothing terribly sophisticated. It's just a listing of files essentially. When you go to that URL, you'll see a series of directories, and we'll be adding to these as we go along. Are you seeing those okay?
I didn't look.
Are you able to see the directories or no? Do you still see the lecture slides?
Yeah.
Okay. It is a let's see here. This thing won't, I guess it's trying to protect me and prevent me from tabbing to something that I don't necessarily want to share, I suppose. But let's try that.
Yep.
All right. So you'll see a list of directories. We'll add to that. You'll see one for homework once we get our first homework assignment out. You'll see one for quizzes when we start doing quizzes. There will be one for exams when we start doing exams. So all the information is distributed from here. A copy of the course syllabus is available under the info directory. So you can pull down a copy of the course syllabus. Normally when we meet in person, I'd hand you a copy of that, but you can download that. We'll go over it. I'll share a copy of it on the screen when we go over it. And then you can find our lecture notes under the lecture directory. This is lecture 1, so you can find that there. And there are 2 files under here. One's just lec01.pdf. That's the same set of lecture notes that you're seeing on the display. It's full color, full format, all of that. So if you're viewing it on a tablet or a laptop or something like that, that'd be the one to go for. If you like to have a hard copy, you want to print it out and not take up too many pages, the other copy here, the one with the -6 pp on it, is 6 per page. So it's the smaller slides that you can conserve a little bit of paper with. So if you want to print them out, that would be the one to go with. So let's see here. Let's go back to the PowerPoint here. That's where you can get our course materials. Let's go over to the course syllabus and we will take a look there. There it is right here. All right, so this is the same as what you can download from the class website. It's got our class title here, Spring 2021. My contact information's here. You all know my email address and such, and you all also know that you can probably get to me more easily by my cell phone than by calling the hangar. The hangar supposedly will get to my desk one day. I don't even know if they've got that set up yet. I haven't been over there in a few weeks, so it's the cell phone's probably the best way to get in contact with me. Send a text or call. Pretty much any time is fine. I don't if I'm busy or if I'm asleep, I probably won't answer, but leave voicemail or leave a message and I'll get back to you on it. And students in the past in this class have made a lot of use of texting me things, and it's something I encourage. If you're working on a homework assignment or something like that, or you're trying to study for an exam and you come up against a problem and you don't know where you're going wrong or if the setup looks good or anything like that, take a picture of it and send it to me. Ask me to take a look at it. As I've got the time, I'll take a look at it and let you know where you might need to make some changes or if everything looks good. That way you get kind of an instant feedback and can proceed rather than having to beat your head against a wall for hours on end. Not to say that it isn't necessarily valuable to beat your head against the wall for a little while. Some of that struggle is certainly necessary, but there becomes a point where it becomes counterproductive. So if you've really genuinely tried to figure out where things are going wrong and you just can't get it, take a picture, send it to me, and I'll try and debug it for you. There's our class times. Those are the default times that they've given us. So basically the first hour and a half of class each night, something like that, hour 15 minutes, hour 20 minutes is our lecture. And then the remaining time a little bit less than an hour, is our practicum, our practical time, where we'll be practicing on problems. And then we are supposed to be at the training center, the new training center, but of course we're having issues with our certificate of occupancy right now. If for some reason throughout the semester we need to go to Zoom, either for some reason we can't be in that classroom, or there's something else that comes up, then we'll meet online. So I've given you the links on that. I've got those also in the lecture notes, so you can copy those down. That meeting information won't change for the semester, so it'll be the same one each night. Let's see here. So our course descriptions. Here's the basic description of what the course is. This course introduces the statics and strength of materials while emphasizing their uses in practical design situations. Topics include unit conversions, force vectors, moment of a force, equilibrium of concurrent and coplanar force systems, stress, strain, shear, and bending moment diagrams, and bending and deflection of beams. So there's a lot of words there. Essentially what we do is we have the course divided up into two major sections. The first 2/3 of the course centers around what we call statics. Statics is about solving problems, figuring out for a given structure and a given load on that structure, how does that load distribute? When we hang a weight on, say, an engine hoist, how much of that weight is carried by each leg? How much is carried by the hydraulic cylinder? How much force is involved? Are those forces pushing things together? Or are they pulling apart? That's the first step in design. When we have to design a structure, we have to have some idea of what the forces are when we put a load on that structure, whether it's a load being a truck on a bridge, or whether it's a load of flight like the lift a wing produces. We have to have some idea of how that force is distributing and how much force we're talking about. That leads us into the final third of the course, which is strength of materials. Strength of materials is about how we pick what materials we use to build the structures we need to build. So we may have figured out how much force we need to support. That when I hang this engine on this hoist, this beam is handling a force of 400 pounds. Well, if I'm going to build this out of aluminum, how thick of a piece of aluminum do I need to make that happen and have it not break? Or if I'm going to make it out of steel, how thin of a piece can I get away with? What should be the size and the shape of the materials that we make these things out of? That's the next part of design. Once you've figured out what your loads are, you have to then figure out what materials do I use and in what sizes and shapes so I can support those loads. And we'll look at a number of aircraft examples specifically on this. One of the things we'll look at when we look at forces in shear is we'll spend a good bit of time looking at rivets. And some of you are in sheet metal right now, and you'll be heading toward putting rivets in and such. And one of the things you'll learn is that rivets are loaded in shear. You'll learn how to figure out from the 4313 and from other resources how many rivets you need in a lap joint. We'll figure out where all that came from in this class and looking at the strength of those basic materials. So some pretty practical sheet metal problems are solved in this particular class. I'm not sure if it's still listed or not, but the materials for the course, they may still have it flagged as being a required textbook. Don't buy the textbook. I haven't put in an order for a textbook or anything like that. I usually treat the textbooks as optional. They're very expensive usually, and they don't add a whole heck of a lot, at least in my opinion. You can go to pretty much any library and pick up a copy of any strength of materials or statics book, and you'll find the kinds of problems that we're going to be solving here. You can buy, cheap used ones on Amazon and such for a couple bucks. If you have a book that you're looking at, if you really feel like you want a book for the class, if you're not sure if one applies, send me the link for it and I can tell you if if it would be a good book for this class. But you shouldn't have to spend more than, I'd say, $10 on a textbook to help you out with this class. Usually students find that between my lecture notes and my examples, we really don't need a textbook, so I usually don't bother with it. Scientific calculator. You will definitely need a scientific calculator. Whatever you used in the A&P program will be fine. It will have to be able to do trig, as we'll be seeing here one of the biggest applications, practical uses of trigonometry in any application. So that's there. Attendance. Well, in a sense, attendance is required, but in another sense, it's not. Attendance, I'm pretty flexible on attendance for the most part. I wouldn't be making these videos available on YouTube and such otherwise. The only things I can't be too flexible on with respect to attendance are our exams. When we have our exams and our quizzes, those are intended to be done in person. And as long as we're allowed to do those in person, we will. So if for some reason you can't make it to a night when we have a quiz, don't worry about that too much. As I'll get into in a little bit here, quizzes are not, they're not weighted for very much. And I think I dropped the lowest 2 quiz grades. So it's okay if you miss 1 or 2 here and there. Not going to be a big deal. The exams are a little bit bigger of a deal. If for some reason you can't make a night that we have an exam, and I'll always announce those at least a week, usually a couple weeks in advance. We'll have to make arrangements separately so that you can take the exam ahead of time, and you'll be taking a special version of the exam so that there's no issue as far as communication with other students. Not that I'd expect anyone to necessarily do anything like that, but I have to take the precaution. So there are potentials for doing an exam outside of the regular class time, but it has to be done before we do the actual exam. No one's going to get extra study time out of trying to take the exam at a different time. Now, of course, emergency situations, we can try to deal with anything, but you can expect that if there's an emergency that comes up, we'll try to deal with it, but we'll also try to verify that things are actually what they seem to be. So that's the attendance blurb there. Homework, we do have a fair amount of homework. We typically have homework assignments once a week. Usually I give them out on Wednesday nights, and then they're due at the end of class the next Wednesday night. So we won't have our first homework assignment till next week. And that covers what we'll be covering on Monday and Wednesday. Usually on Monday night, I'll ask if there are any questions on the homework, and as the homework assignments get more challenging, I will expect questions. There are some problems I put on the homework that I expect people will be asking questions on, and would be surprised if questions weren't asked on them. Usually on a Monday night, I'll kind of give you a basic idea of what the approach should look like, but I won't exactly solve it for you. On Wednesday night, before the homework assignment's turned in, I give the class an opportunity to collaborate with each other a little bit and decide on one question on the homework to have me work out in full detail. And if you happen to copy down what is worked out and turn that in, you'll get credit for it. So if there's a particularly tough or challenging problem on the homework, there's an opportunity there for the class to get together and put effort into it, but see it worked out. Late homework, not accepted. So the homework does have to be turned in on time. It's turned in at the end of class. If for some reason we have to go to a situation where we're online, scan an email or copy or text would be fine for that as well, for submission of the homework. Going back to attendance for a moment, this is not an FAA course, so there's not missed time and makeup time or anything like that. This is a regular college class, so don't worry about trying to make up time. You are responsible for what you missed in class. So it's worthwhile to either find out from someone or go check the YouTube video to see if you missed anything that you needed. Let's see here. Quizzes and exams. We'll have several quizzes, usually about once a week. We'll have a quiz. I think we have 6 to 10 quizzes throughout the semester, depending on timing and such. Typically on Monday nights during our practicum session, we do our quizzes, and they're usually on the homework assignment that was submitted the previous Wednesday. So we won't have our first quiz for a couple weeks, and I'll announce it ahead of time, but it's based on the homework assignment that you will have just gotten back on that Monday. So you'll have a chance to review your homework there. So there's plenty of opportunities to fix problems as they come up. Lowest 2 quiz grades will be dropped, and exams will have 3 exams throughout the semester. Typically, I'm a little bit shifted here because we started off a little bit of different time, but I would expect our first exams probably going to be sometime around mid-March. Our second one's probably going to be probably early to middle April. And then our third one's going to be pretty close to the end of the semester in May. So, and I divide up the class kind of conceptually on that. So there are pretty good division points where we have exams. So we'll be leading up to that, and you'll know exactly what material is covered on each exam. Each exam is worth a fair bit, as we'll see here in a little bit. So it's worth putting some time into it. I will always post a practice exam with solutions, so you can see an exam that has been issued in a previous semester, and that you can try out on your own and check against the solutions. So you'll have plenty of opportunity to practice things. There will always be some last minute question time prior to the exam. So, and if we do the exam in person, the last class missed out on 2 of these, 3 of them really, but we normally students are cramming for the exam in the half hour between the A&P program and our class. So I usually leave that gap there so people can go out and grab a bite to eat or something like that before class. So on exam nights, to make sure there are no distractions or to allow you to have that extra study time if you want to, I bring food in. I'll be providing pizza for the class on exam nights. So as long as we're meeting in person, I can't quite do that if we are relegated to being online like we were last semester. But hopefully we'll be doing things in person, and I'll provide a couple pizzas for people to sustain themselves through the ordeal of the exam. There will also be a comprehensive final exam. Now, each of the 3 exams during the semester, they're just on the material since the previous exam or since the beginning of the class. The final exam is comprehensive. Final exam covers everything, and it's a pretty traditional 3-hour final exam. If you know what you're doing on it, you can get it done in an hour and a half, 2 hours. They're usually 9 to 10 problems, things like that. And it covers every major topic we covered in class. So if you've had college classes before, it's nothing atypical. It's a pretty standardized kind of final exam. We do have a lab project that we'll see how much we can make use of this semester. Where we do this in strength of materials, we set up a little bit of an experiment. We build up some structures, and then we go over to Utica and use their 200,000 pound load frame to apply stresses to it till they break, and see if our predictions match the strengths that we expected, so that we actually achieved. So we'll see if we can do that. We weren't able to do it last semester, and in fact, we haven't done it in a few years because it seems like every time we get ready to do this, their machine is broken. So maybe we'll be able to get everyone over there this year, especially with a small class. Let's see here. Grading, straight scale. We've got so unlike the A&P program, it's just on the regular ABC boundaries as you're normally familiar with. Homework's worth about 10%. In fact, exactly 10%. We typically have around 10 homework assignments. So each homework assignment's worth about a point on your grade. So bear that in mind when you're balancing your time. If you've got other objectives or other classes that you really need to put more time into, if you blow off a homework assignment for this class, it's only going to cost you a point on your average, and you'll have some opportunities for some makeup work on that as we proceed. The quizzes all average together another 10%, so they count basically on par with the homework. The lab projects 10%. Each of our exams is worth 15%. So we got 45% on our exams during the semester, and then our final exam's a quarter of your grade. The academic integrity policy, that's the same thing that I showed you in the A&P program. Basically just means do your own work. You'll get farther ahead anyway by making sure you work with you figure things out on your own. It's not a bad idea to work with your fellow students to try to figure things out, but when it comes to actually doing the work and putting things down, there's that line between working together and just copying from someone else. So if you do your own work, you'll generally come out ahead better for it. Let's see. Anyone have any questions so far?
Nope.
Now, our course objectives, these are what we expect you to be able to do. So this is a little bit more about our detailed course content, but this is what we expect you to be able to do at the end of the course. We're going to be dealing a lot with forces. And one of the things you're going to learn about in this class is what we call vector addition, how we take multiple forces and combine them together to get one total force. That's a big application of trigonometry. That's our big mathematical tool, and we'll be reviewing on that next week. We'll be reviewing on how we use some of those tools. So don't worry if your trig knowledge is a little rusty. We'll be working on analyzing force systems, and one of the tools we use for that is what we call a free body diagram. Free body diagrams help us to clarify what forces are acting on what objects so that we can more correctly analyze them. We're going to be working in equilibrium. In this class, everything is in balance. Everything is stationary. And we have to figure out what combination of forces is making that happen. We're going to be able to find equations to solve that will tell us what the unknown forces in a problem must be in order to have equilibrium. And so we'll learn about the equations of equilibrium and how to solve them for different kinds of systems. We'll work a little bit with things we call centroids, which since everyone here is in A&P and all of you are past the first semester, the centroid is a generic way of saying center of gravity. It's a way of dealing with a center that's not necessarily about gravity, about weight, but could be about area, for example, or about material distance. There are all sorts of different ideas about where balance points can be. Those balance points don't always have to be about weight. So we'll get to that toward the end of the class. We'll get to another idea called moment of inertia, which has a lot to do with bending and why some things are easy to bend and why other things are not so easy to bend. We'll look at friction and what friction does. We'll look at shear force and bending moment diagrams. Those are ways of figuring out what kind of forces are internal to a beam when we put a load on it. So think about somebody standing on the end of a diving board. That diving board's going to bend. How far is it going to bend? What kind of stresses are involved and what kind of forces are involved inside that diving board that keeps it from falling apart or breaking? That's one of the things we'll take a look at there. And where is it most likely to break? Where is it going to overload first? If we put too much load on it, where is it going to break? So we'll be able to determine that from looking at bending moment and shear diagrams. And we'll look at deflection of beams. And a wing spar is basically a beam. So we'll be able to look at how a wing flexes in flight and changes its angle to the horizontal as we put loads on it. Now, our course is set up for a regular 15-week schedule, and since the A&P program and the college basically started at the same time this semester, we're basically going to be uh, running this course through the end of our spring semester for both A&P and this class. This is only a 15-week class, so you'll be done a couple weeks before the end of the spring semester in May. We'll be done typically the beginning of May. First couple weeks of May, we're done. I think we're done with the A&P program third week of May. This is a tentative outline. I'm not going to go through the details of each week, other than to take a look at the first week. This first week is next week, week number 1. This is sort of week 0 for us. It's just an introduction. Since we're starting on a Wednesday, we don't have a lot of time to really get into some heavy duty stuff. So we're just going to do an introduction. Next week we'll get into the real content, but you can take a look through that and get some idea of how the topics are distributed week by week. It is tentative because it might change as we go and adapt to different things, and I adapt to the class. If the class is struggling overall with one idea, we might spend more time on it, and maybe not as much time on other ideas. So we'll see how things go. Each class is a little different. I've got the boilerplate disability statement here. About the only difference from this one than ones you might have seen otherwise is that they've added some information on COVID in there. So if you have a diagnosis or something like that and you need accommodations, I don't think it's going to be a big issue with this class, but you can get official accommodations through the Office of Accessibility Resources, and the contact information's there. And last thing I have on my syllabus is a modifications clause. If for some reason I need to make a change to the syllabus, I can do so, but I will do so in writing prior to the effective date. And generally changes will not be retroactive, so they won't change what has already been done. They will only change things going into the future. So that is our syllabus, and I have met the objective here of going over the syllabus with the class, which is something that we're required to do by the college. So there we go. Any questions on the syllabus?
Nope.
All right. Adding or dropping. Now, I think everyone who at least is online right now is added into the course. If you know somebody who wants to be involved in the course, point them at the YouTube channel, which I'll give you the URL for here in a little bit, and have them follow the instructions in this video. But they do need to add in. It gets progressively more difficult to add in after the first week or so. The number of signatures you need to get into the class goes up. So at some point there's a final add date where you can't add into the class. On the other side of adding is dropping. If for some reason you decide this class really isn't for you, or you are not getting what you want out of it, or maybe you have decided to change your objectives and want to drop the class, you have plenty of time to do so. The only thing I would advise you to do is talk to me about it first, because sometimes people get into a situation where they think they need to drop because they did really poorly on an exam. Just because it looks bad doesn't necessarily mean it is. And it's not usually something that is unrecoverable. It's something that we can usually work with. So the situation may not be as bad as you think it is. So talk to me before you pull the trigger on it, and we'll see what we can do. We should have, if everything goes according to our regular schedule, we'll have our first 2 exams done by the time the drop date rolls around. Drop date's usually pretty late in the typical fall semester. Drop date isn't until Thanksgiving, so that gives you some idea of about how long into the semester the drop date is. So you can look up in the college catalog when the drop date is, and I'll advise the class on when it is when it comes up. But you've got quite a while. Usually, I think end of March sometime is the drop date. So you've got plenty of time. We'll have our first couple exams in by the time we get there. If you need to add in, the information for adding is here. The if you need to fill out an ad form, the CRNs, the course numbers are 26105 and 106. The title of the class is Applied Mechanics and Strength of Materials, and the section number is K10 and K11. And you can do that all in one ad form. Most of you are here because you already did that, so it's not too difficult to take care of. But if you need that information for adding, grab an ad form, fill it out, and bring it to the office. If they say you need a prerequisite or something like that, let me know, and I can sign you into it. Textbook we already talked about, so no worries on that. Don't buy a textbook unless you feel like you need one, and I wouldn't advise spending more than about $10 on one. So these statics books are everywhere. You should be able to find hundreds on eBay or on Amazon for under $10. That will be more than satisfactory. Second page of administrivia, I suppose. The class website, I've already shown a couple times here, but there you go, MT225 at keytool.org. That's our course website where I'll distribute everything from. A couple other URLs that are new. This is not something that has ever been really in this presentation before, but something I had to add last year as we dealt with our pandemic shutdowns. I've created a YouTube channel for this class, and that YouTube channel does have videos from last semester on it as well. So there will be, as we build up our inventory of lecture videos and lab videos for this semester, you'll have last semesters that you can go to for other problems or other practice or other discussions. If you just want to see it again in a different with a different tone or something like that, you can probably find those. But the YouTube channel's there. It's a big long URL, so I ran it through tiny URL. So there it is right there. There's nothing up there right now except what was up there for the spring semester from last year. I'll be posting this video sometime tonight. I'll probably upload that before I'm out tonight. So that's our YouTube channel. And the Zoom information that I emailed everyone today is also here in the class notes. There's the URL for the Zoom meeting, and there's the meeting ID if you need that broken out to dial into anything. So that won't change. That's set up for the entire semester. So anytime we need to go to Zoom, those are the numbers for it. All right. Any questions there?
I got a question about, say we do want to drop it. Not
Yep.
saying we do, but will it affect the financial aid or affect the A&P program?
It shouldn't. It's I don't know all the details about how financial aid works, but as far as enrollment is concerned, you're a full-time student already.
Mhm.
About the only time it becomes a problem is if somebody drops it and it changes their status from full-time to part-time. But everyone who's in the A&P program is a full-time student already with just the A&P program classes. There's some interaction somewhere with financial aid, and I guess they put some credit hour limits on how much financial aid you get total throughout your certificate or your degree program. I'm not exactly sure what those limits are, so you might want to talk to somebody about that first, but I don't think that I don't think it has a significant enough effect with just one class.
Right.
Any other questions there? All right, so everyone's seen most of this part before since we've done this in the A&P program, but basically what do I expect of you as students in the class? Academic integrity first and foremost. Like I said, again, it's okay to work together. It's okay to bounce ideas off each other or see what your approaches are, but don't cross that line into just copying someone else's work and having no idea how to do it on your own. It might help you during for the homework, but remember, homework each one's worth 1 point. The exams, it's not going to help you on. So you got to learn the material eventually to be able to prove yourself on the exam. So it's better to do so on the as you're working with the homework. But keep that academic integrity up there. Professionalism, just like in the A&P program, I do expect our students to behave professionally and conduct themselves, respecting each other in the class and the environment and so on. I do encourage interaction. I do expect interaction. It's a little hard when you're doing this asynchronously. If you're watching the videos and you're not able to really interact directly there, but if you happen to be watching this as a video later on, and a question comes up, pause the video and text me or call me, and I'll see what we can do. Especially since I'm not teaching in the A&P program right now. I'm usually out and about during the day. So if something comes up, I'm usually working on something. I can go on speakerphone and keep on working. So if you got a problem, question, concern, feel free to call or text, and I can likely get back to you pretty quickly. This class is kind of like the A&P program in the sense that it starts off kind of slow, but the intensity builds up each week as we add ideas and concepts on top of what we previously built. So effort's pretty important. It's important not to become complacent early on and think the whole class is going to be basic, simple math, and keep that effort up and make sure you're developing your skills so that when we do get to the harder stuff and start putting in a lot more time and effort, when our homework assignments drop from being 10 problems to being 2 problems, that will take the week to work out. Keep on plugging away at it. It will pay off. It does help if you like solving puzzles and things like that. That's a lot of what some of these early concepts and such can kind of seem like is problem solving. Some of it can get a little tedious here and there. That's engineering work. That's why we write computer programs to do this stuff. But we've got to learn how the computer programs work. So that's a lot of what we'll be doing. But keep that effort up and it will pay dividends. And then on the other side, what I think you should expect of your instructor in this course, on top of the list is always quality instruction. What I try my best to get you, no matter what the medium is. The feedback, I try to keep as prompt as possible, just like in the A&P program. Usually with homework assignments, when they're turned in on Wednesday night, I will get them back to you on Monday. Same thing with exams when we're done with. That's why I usually have them on Wednesday nights, so I have the weekend to grade. Quizzes we usually do on Monday nights, so I have to scramble a little bit to get them graded before Wednesday night. But with 6 or 7 of us, it shouldn't be too difficult to deal with. So you should be able to get relatively prompt feedback on your graded material. You always have the option with other material or other questions to just text or call or ask a question in class and get instant feedback. Fair evaluation. I try my best to make sure I evaluate everyone the same way. I've got standards on what my grading looks like, and you'll be able to see that this semester. The A&P program, you weren't able to really see that because I didn't release my solutions, but every time we have a homework assignment or a quiz or an exam, I'll post the quiz or the exam and the homework, and I'll post my solutions to it. And in each problem, there are notations about how much each part's worth, what partial credit is given, and so on. So you can see what the standards are and you know what you're being graded against. There is always some degree of interpretation. And I always encourage people, if you think you've been treated unfairly, certainly raise a question. I'd be glad to try to alleviate your concerns. I do also usually tell people that I don't put down numbers or anything else on paper that I'm not willing to defend in court. So expect that if you've got a question about how many points I took off of something, I've got a reason behind it and I'm willing to defend it. So feel free to ask, but don't expect to just say, okay, well, you asked about it. Okay, here's your credit back. We will have a discussion. It's not to say no one ever gets credit back, but there has to be a good argument there, I suppose. Responsiveness, that's to me about making sure that if you have a problem or concern or an issue either with the material or the class as hole or really anything else, that I'm able to respond to that and adapt to that situation. And a lot of that is availability, just making sure that that I'm accessible and available to be able to meet those concerns. And then finally, assistance. My job here is to help you learn the material and to see its application and develop your skills. You have to put the work in. I can't do the work for you. I can show you the door, but you have to walk through it, so to speak, to quote a movie, I suppose. But that's my primary role here, is to help guide you through the information, give you some examples, and let you try to figure it out. So those are the expectations. Any questions there?
Nope.
Now, I usually joke in the A&P program, free food is not an expectation. In this class, it usually is. So just for exams, though. All right. So the little bit of content for tonight is about the idea of mechanics and what mechanics is. So not mechanics in a maintenance sense, but in a physics sense. Mechanics is a branch of physics in which we study the effects of forces on bodies. So we push on something, it moves. How does it move? What direction does it move in? How fast does it go? Does it speed up? Does it slow down? Does it change direction? What's the result? That's what mechanics looks to solve. Mechanics also handles situations where we apply a load to something and we don't move, or it doesn't move, or we want to support it. We want to jack up a car, jack up an airplane. Where do we have to put those jacks, and how much force do we have to apply to oppose gravity? Those are problems that are solved in mechanics. Now, mechanics is a really broad subject area, and it covers everything from things we'd see in our everyday lives to atoms and molecules to stars and galaxies. It's a huge range of topics, and it's divided up into different subtopics. What we look at is what physicists would call classical mechanics. Classical mechanics is mechanics that is governed by Newton's laws, or at least Newton's laws explains. And so we'll review a little bit on what Newton's laws are here tonight. Classical mechanics, we have the concept of inertia. Inertia is about what we call today mass. Everything that we'd exert a force on or have a force exerted by has some mass to it, and that mass has an influence over the motion. We have the idea of acceleration. Acceleration is the rate of change of speed. It's how fast or slowly something gains speed or loses speed. In the A&P program, we talked about it in terms of things like race cars. In a race car, you get a 0 to 60 time. For example, that's the time it takes to get from 0 to 60. It's not that we get from 0 to 60, it's that it does so in a certain amount of time. That's acceleration. A fast or a sports car might be able to accelerate, high-end sports car, be able to pick up 0 to 60 in 2 seconds. Not so advanced car might take 10 seconds. So acceleration is about how fast we pick up speed or how fast we lose that speed. If we think about things like braking, how quickly can we slow down? How fast can we go from 60 to 0? How much time is that going to take? So that's the idea of acceleration. And then we have the concept of action and reaction. And so each one of these major ideas is handled by one of Newton's laws. Action and reaction is going to become very important to us in this section, in this class. We'll have a whole category of forces that we call reaction forces that are very important to work with because they tell us about what supports the structure that we're dealing with. And those reaction forces can become pretty significant. So when we went over physics in the airframe and power plant program, we went right down the line. We talked about Newton's first law, then we talked about Newton's second law, then we talked about Newton's third law. Well, at the time, even though my notes said Newton's first, second, and third, I argued that Newton's second law is really the most important one. And so since this class is more about engineering and engineering principles, I'm going to start with Newton's second law, start with the more important one. Newton's second law is the relationship between acceleration, force, and mass. That's how those three quantities, those three concepts are tied together. Now, Newton, as well as a lot of others, came along and knew there was some relationship there, that when you pushed on something, it sped up. When you pulled on it, maybe it slowed down. If you pushed on a heavy thing, it moved differently than if you pushed on a light thing. That there's some relationship between force, mass, and acceleration. Newton was really the first one to write it down, and to write it down in a sense of an equation and a definition, really, of acceleration. It was really the first time acceleration was rigorously defined. And this was how he wrote it down. This is acceleration A, is the ratio of force to mass. So if you want more acceleration out of something, you can either push on it harder or make it lighter. If you have a smaller amount of mass, you get more acceleration given the same force. If you have the same mass and you push harder on it, you get more acceleration. So think about airplanes and taking off. If you have a fully loaded airplane, those engines can only produce a certain amount of thrust. So the airplane's going to take some time to accelerate. It's going to have a pretty low acceleration. If, on the other hand, we have no weight on board, we don't have any cargo, we've got minimum fuel, we've got very light aircraft, those engines still produce the same amount of thrust. So less mass, more acceleration. We get up to our takeoff speed in almost no time. So acceleration depends on not just how hard we push on something, how much force we apply, but how much mass is involved. Then we have Newton's first law. Now, Newton's first law, we said in the past, was that objects at rest stay at rest and object in motion stays in motion unless acted on by an external force or an outside force. What Newton's first law, the simplest way I could possibly say Newton's first law, is to say that there is no acceleration. That's about the simplest way to state Newton's first law. Whenever there is no acceleration, we have Newton's first law in play. Newton's first law models the situation. And if you think about what no acceleration means, no acceleration doesn't mean no speed. It means no change in speed. So zero acceleration means that if something's traveling down the highway at 70 miles an hour, and a second later it's still going at 70 miles an hour, there's been no change in speed. There's no acceleration. Now that also does apply to things at rest. If I've got, my mouse sitting here on the table, it's not moving right now, and it's still not moving. It's stationary. Its speed isn't changing, so it's got no acceleration. Things at rest automatically have no acceleration. If something's moving, it can still have no acceleration, but it has to be at a constant speed. So an airplane in straight and level flight. When an airplane's in straight and level flight, it is moving at a constant speed. There is no acceleration there. So that's the idea of Newton's first law. And Newton's first law is going to be of huge importance to us in this class because every system we look at is going to be modeled by Newton's first law. It's always going to be a situation where we have no acceleration. That is what we call statics. Statics is the division of mechanics that studies systems that have no acceleration, that are governed by Newton's first law or modeled by Newton's first law. So if you think of a bridge, for example, a bridge is stationary. It's not moving. It's a bad day if that thing starts accelerating. If a truck goes over it and the bridge starts accelerating, it's a dramatic situation. That is not what we are interested in this class. In this class, everything is static Everything is stationary and has no acceleration. So this actually falls out of Newton's second law, which is why I treat Newton's second law as more important, because it has Newton's first law buried in it. If we say the acceleration is 0, or if we say there's no net force, all the forces that are acting on something counteract each other, like in an airplane in flight, lift and weight oppose each other, thrust and drag oppose each other. If those are all tied up so that we have exactly the same amount of lift as we have weight, and we have exactly the same amount of thrust as we have drag, the net force is 0. And if there is no net force, then when we divide that by the mass, we get no acceleration. That says that either that thing's going to be stationary or it's going to be moving at a constant speed. If I have a weight sitting on a table, there is no net force there. It's stationary. There's weight pulling down, but the table is pulling up, is pushing up, balancing out that weight. So there's no net force. And that's going to be the big important idea for most of this class, is that in every situation we look at, no matter how many forces we've got, when we add them all up, they'll add up to 0. For every force, there's an equal and opposite force balancing it out. So in a sense, every problem that we solve in this class is about balance or about equilibrium. And equilibrium means no net force, no acceleration. So that's Newton's first law. And then we have Newton's third law, the law of action and reaction. And what Newton's third law tells us is that if you push on something, it tends to push back on you with the same amount of force. Same force, opposite direction. The biggest issue with Newton's third law for us is sorting out what bodies forces act on. Because it can get a little confusing sometimes when we look at a system to figure out, well, what's a force and what's just a reaction? What is pushing back on the object and what is the object pushing on? The free body diagram helps us to sort that out a little bit and maintain some clarity on what forces are acting on what. But we do know from the law of action and reaction that every action has that equal and opposite reaction. Every application of a force is counteracted by another force, by that reaction force. So we'll see how that applies when we start looking at structures. So that's statics. Statics is the main division of mechanics that we'll be working with this semester. Statics is the branch of mechanics concerned with bodies in equilibrium, in balance. And if a body's in equilibrium, the total force on it is 0. Now, when we deal with total forces, we have to take into account direction. And I gave an example of this in the physics class in the A&P program. If you're pulling to the right on something with 100 pounds of force and there are no other forces acting on it, that's a net force. You got 100 pounds of force pulling to the right. But forces have direction to them. If we put another force in pulling to the left, that's going to counteract the force pulling to the right. If both forces have exactly the same size, but opposite directions, then we can add them up much like we'd add up signed numbers. We can say the 100 pounds to the right is positive 100. The 100 pounds to the left is negative 100. And when we add positive 100 and negative 100, we get 0. So when we put signs on the directions for forces, positive usually to the right and up, negative to the left and down, when we put our signs on and we put numbers on all these and we start adding them up, if a body is in equilibrium, that total force must be 0. In fact, we usually turn that around. We say, we know this body is in equilibrium. So the forces, when we add them up, must be 0. So how much force do we need to apply right here on this system in this particular way to make sure it's going to be in equilibrium. So we can turn that idea of equilibrium around into a set of equations that we can solve to figure out unknown forces. And those will be some of the first practical problems we'll solve once we've worked out some of the mathematical preliminaries. So statics is about the application of Newton's first law. The first 9 weeks or so, the first 2/3 of this course is all about statics. So we'll be building tools to analyze static problems, and that'll start with some basic math review, some algebra, and some unit conversion issues, since we have some issues here with changing units from one to another, and that's one of our objectives in this class. We'll deal with both metric and standard problems, so we'll have to deal with both of those. The goal is usually to figure out ultimately how structures distribute forces. And the big example of that is what we call a truss. And I want to give you a brief example here. And normally I'd go to the whiteboard and do this, but I guess I'm just going to have to draw. And whoops, that wasn't the right button. Where did my drawing tool go here? Let's see. Well, that's interesting. This is not the usual version of PowerPoint that I use, so I expected to be able to. I can do a laser pointer, but I can't. Apparently, can't draw on the screen. But if you think about, all of you have been in the hangar, so you've all looked at the ceiling and the roof inside the hangar at some point. That whole structure up there is what we call a truss. And a truss involves a bunch of different pieces put together. If you've done any kind of construction or anything in homes and such, you may have run across trusses in those kinds of builds as well. But it involves connecting together various pieces that we call members in different shapes and sizes and different angles, so that when loads are applied, those forces are distributed through the structure and eventually to the supports that those trusses sit on. We can build bridges out of trusses. There are plenty of truss-shaped bridges around. If you think of a typical train bridge around here, like a bridge that a train would go over, if you happen to drive on 5S on the way toward Ilion and Mohawk, Frankfurt, that area, there's one right there just before Dyke Road, I think. That's a pretty good example of a truss bridge. And by interconnecting all of these various pieces, we build up a structure that can handle a good bit of weight and span a pretty good distance. The hangar, we're able to span a pretty good distance without having to have supports in the middle because of that truss structure. Now, the truss has to handle the weight of the roof and the snow that might be sitting on top of it. Snow load, I think 20 pounds per square foot of force has to be handled, and all of that has to be conducted through that structure to the ends where it sits on the walls, and the walls can conduct that down. The truss is a tool for changing applied forces and conducting applied forces into the supports, and each piece of that truss carries some of that force. Some parts of the truss carry more force than what's applied. In statics, we will break apart a structure like that and figure out how much force does each piece contain? How much force does it handle? Is it being pulled on? Is it in tension? Or is it being pushed on? Is it being squished? Is it in compression? And that can change with the load that we apply. So even though we might be dealing with the same truss, if we apply different loads to it, different members, different parts of it will have different amounts of load on it. And that's what we're typically trying to solve. That's our ultimate problem. That's what we're going to be building toward over the next several weeks, and over the next basically 9 weeks, we'll be building toward solving truss problems. The other part of dynamic, or part of part of mechanics is what we call dynamics. Dynamics is about motion. Motion is not going to be part of this class. So everything we're dealing with is static. We have to get the statics right before we can deal with dynamics. So all of our application is going to be on statics. So dynamics is about motion and Newton's second law, not covered in this course. It would be a next course, that a subsequent course that you'd take. And then we've got our last third of the course. We've got strength of materials. Strength of materials is about figuring out, now that we know the loads, now that we know how those forces are distributed, what materials do we need to actually make this structure work? If you've ever been involved in building something, building a house, for example, you may have had to pick lumber. Well, lumber comes in lots of different sizes: 2x4, 2x6, 2x8, 4x4, or 6x6. You may have had to pick lumber to use. Well, that lumber is shaped and sized differently to handle different loads and in different directions. Some work great for walls and posts, but as long as you don't space them out too far. If you have to space them further, you need a bigger piece of lumber. So statics tells us about what the forces are, but it says nothing about what materials we use. That's another decision that we have to make, because materials have limits to them. Materials have points where they can fail, and they have limits to their strength. We have to be able to deal with that. We have to be able to figure out, well, what size do I pick? What material do I pick, to make sure that the loads I'm going to get in this structure are never going to bring this material to the point where it could fail. Very important in aircraft. For those of you doing sheet metal now, when you do a lap joint, you need to make sure that when that lap joint is put under load, that the rivets aren't going to just shear right out. We need those rivets to be able to hold a certain amount of force. How big do they need to be? What spacing do we need on them? How many rivets do we need? All of those are questions that we can answer once we understand both the forces and the materials. So the first 2/3 of the course focuses on figuring out the forces. The last third is about figuring out the materials that will handle those forces successfully. So the materials strengths tell us about how that structure will change as the result of applied forces. We want it to change very little. We don't want it to move very much. Chances are most of you have had some experience where you've gotten up on top of something or walked into a structure and it really just wasn't as strong as you thought it was. Maybe it felt a little wobbly, or it moved a little bit more than you expected, and you maybe thought, hey, I'm in danger here, or I'm not going to get up on this. That's what we're looking at with strength of materials. If we pick materials that are too weak, things tend to move. They might just stretch out, or they might break. And we need to figure out which is going to happen and how we can stay away from those points. So that's what we'll be focusing on in the remaining part of the course. And one of the biggest examples we'll do is tensile testing, where we basically take a piece of material and we pull on it until it breaks. That helps us to figure out what the strengths are in those materials. I'll have some examples that I'll be able to show you when we're able to meet in person, of different bars that are stretched out. I've shown some of you these when I did material science, but with you. But if you didn't have that course with me, I'm not sure if you saw it or not. But we can take pieces of 1/4-inch thick plate steel and pull on it until it breaks. Takes 80,000 pounds or so to do, but eventually it breaks. It stretches out a heck of a lot before it does. And so we'll see that kind of behavior and how that works. So that's the idea with the tensile test, and we'll where we basically pull on a part till it breaks. That tells us about the critical strengths and tells us how much we can load it before it's going to have problems. So that's the basic content here for the evening. basic ideas about what the course is about. So hopefully now you have if you didn't have any clue as to what this course was about, now maybe you've got some idea, and we'll develop that idea as we proceed. I always finish up the lecture notes with a preview of what we're going to be doing next time. And next time we're going to start a 2-part review of basic math that we need for this course. So unlike the A&P program, we are not starting with addition and subtraction. We're going to assume you're okay with that. We'll basically be starting with a little bit of algebra and some algebra skills, solving equations, some things we may not all be familiar with. If you haven't had some more advanced math, you may not have dealt with solving what we call simultaneous equations, 2 equations with 2 unknown quantities. We'll get into that on Monday and see how that works. And then Wednesday, we'll be doing a little bit of trig review and getting those ideas down. We'll do some unit conversion practice and look at those. So a smattering of various mathematical topics to make sure everyone's on the same page. And then we'll, starting a week from this coming Monday, that's when we'll get into some real physical problems. We'll start solving some problems once we make sure everyone's got the requisite mathematical tools. So let's see here. Whoops, that was, I have no idea what I just did there. Let's see, we'll end the sharing there. There we go. All right, well, looks like we still have everyone. So either everyone fell asleep or they're muted out for a reason. That's okay. Like I said, attendance isn't required in that sense. Anyone have any questions?
Nope.
Nope.
All right. Oh, Phil's still with us. All right. So if there are no questions, then have a good night, and I'll hopefully see you in person on Monday. I'll be in contact by email if anything changes. By default, we'll stick with the Zoom session. So if you don't hear anything from me by Monday, we'll meet right back here in the same format. I'll have my document camera then, so I can draw some stuff out live for you. But hopefully we'll have our certificate of occupancy, or I'll have a room on the Rome campus that we'll be able to use, and we'll meet in person. But I will email you as soon as I know if anything changes. But let's leave it as default. We'll be back online. All right. Have a good evening.
You too.
Thank
Have a good
you.
night.
Thank you.
Good night.